Okay, so we have derived the average expression for the two-port network of the I1 average and I2 average. And in this section, we are going to utilize the mathematical model to plot its equivalent circuit model. So we are going to analyze the equivalent circuit. So for a general two-port network, including the two switches, we can plot it in a universal manner. So here is the active switch MOSFET and the diode. And we can mark the input port quantities and output port quantities. So input, the voltage is V1, current is I1. And output port, the voltage is marked as V2, and current is marked as I2. Those quantities are time varying, right? So based on the example we have used in the previous section, we have derived the input port and output port equations for the extracted switch network. For example, the input port, we have the average input current equals D1 squared times Ts over 2L times V1 average. And if you look at this formula, you will see that the input port voltage is kind of proportional to the input port voltage, right? So this is indeed a resistor behavior, because Ohm's law tells us that for a resistor, the voltage and the currents are proportional. So the effective resistance can be derived as the inverting of this coefficient, right? So 2L over D1 squared Ts. So, but this is not a real resistor. This is a kind of virtual resistor. So this means that for the input port, we can model it as a virtual resistor accordingly. So here is the average input port current, and here is the input port average voltage. So the MOSFET is kind of modeled by an effective resistor who is a function of the duty cycle. And next, let's look at the output port. So previously, we also derived the relationship for the output current, I2 average. So here I'm coupling the results we derived in the last subsection. It equals to D1 squared Ts over 2L times V1 squared over V2. We can do some operations to this formula. namely by multiplying V2 average on both sides. So the left-hand side will be the product of currents and the voltage. And the right-hand side will be this part. So this is indeed 1 over effective resistance. And here is we keep it as V1 average square. So RE is a function of duty cycle. So interesting thing is that if you look at the result here, the left-hand side is the product of output current and voltage. So which indicates a power source behavior. So this is equal to the power of the output port, right? Output port. So this means that we can treat the output port as a dependent power source, right? Dependent power source. So meaning that the output port has a dependent power source behavior, so that we can model the output port by a power source. So the power is indeed, right? Indeed, if you look at the right-hand side, this is the V1 square over R. So meaning that the power absorbed by this virtual resistor. So this means that the power from the power source is coming from the power absorbed from the virtual resistor. So we use a arrow to show that the power transferring relationship. Because we consider the switch network are fully ideal, so there is no internal power loss, right? So all the power absorbed from the virtual resistor is fully transferred to the power source on the output port, output side. By doing this, we can fully establish the equivalent circuit model for this switch network. And I'd like to clarify that this obtained equivalent circuit is universal, right? It can be applied to different topologies, not only the buck boost, but also the buck boost SEPIC choke converters. So next, let's come back to the DCM buck boost example, right? So we look at the average model of DCM. Buck boost. So we can first plot the circuit components besides the two-port switch network. So here is the input source average. And here is the switch network, right? Here is the inductor L. And here is the filtering capacitor C. Load resistor R. And here is the output signal, V average, TS. Internally of the rectangle, right, it is indeed the switch network. And the analysis here tells us that we can replace the switch network by its equivalent circuit of a virtual resistor and a power source, right? So we just plot the equivalent circuit into this rectangle. So here is a virtual resistor. And here is the power source. And power is transferred from the virtual resistor, right, P. And this is the effective resistor, right? So this is much simplified, right? And the previously nonlinear switch network is replaced by this equivalent circuit. And based on this model, we can do the DC analysis. So for large signal DC analysis, we would consider that the inductor will be equivalent to short circuit. And the capacitor in DC will be equivalent to an open circuit. So we can simplify, right, or modify the schematic. So this will be short. This will be open. So the resulting DC model can be solved to analyze the DC relationship. For example, the input port, we can calculate the input power. So input power will be easily to be derived. It's like the input source provides power to the effective resistor directly. So the power will just equal to the input voltage squared divided by the resistance of RE. And for the output port, we can calculate the output power, which is actually the power absorbed by the load resistor. So equals to output voltage squared over load resistor R. Based on the principle of the energy conservation, so those two quantities, they should be equal on right-hand side, right? So therefore, we can derive that. So we can derive the relationship between the output voltage and the input voltage will be equal to minus sign, mainly because buck boost is in inverting topology. So square root R over RE, where RE is the effective resistor. So next, we can plug in RE, right? Plug in. RE expression into this formula. So we will see that the voltage conversion ratio of V over Vg equal to minus RE equals to this quantity. So square root D squared. So this is large signal DC, so we replace D1 by capital D here. Ts R over 2L. equals to minus d over k. K is a parameter which we use to simplify the expression, right? So where k equals to 2L over RTS. So you will see that this obtained large signal DC voltage gain is identical to the previous derivation we made when we studied the DCM operation of the switch mode power supply. Okay, so this validates our method here. In this section, we have plotted the DC equivalent circuit model for DCM buck boost converter. And by utilizing the model analysis, we analyzed the energy conversion of the DC large signal. Nextly, we are going to study the AC model of the DCM operation.